And in the code beneath there you have some markers which just say, okay, where you get the idea that you code that. Where is it related to? For small projects, that usually is done by hand. Larger projects, like 4.5 million lines of code, will have some automatics in here. So it's quite good to know, because if you have an inspection of the code, if you just have a look at it, you always know where it comes from. And here we are at the testing. Yeah, as said, if you specify it, you have to verify it also. And the verification heavily depends on the software level. For example, on level E, as said, no testing is required at all. You just code and hope it's working. On level D, you're doing some high-level tests. That means that you test your high-level requirements. There shall be a beer ready function. You write a test case, and if you have written your source code, you can run the test and see if it's there or not. By the way, not always automated tests is the solution to everything. Also, code inspection could be a valuable thing. But as you can imagine, everything you have to do by hand costs even more amount of time. On level C, you also have to do low-level tests. That means everything you have specified in the low-level requirements has to be tested. And you have to have statement, data, and control coverage. Of course, you specify data, and you have to show here that every statement in the code is really required. And every data structure and every control flow has been required. But it gets worse. On level B, it gets independence, and I promise the next slide will be about independence, and decision coverage. That means every decision you do in the code has been inspected and has to be followed. So that every line of code has to be at least one possibility which is used. For example, if you have an if clause with which never will happen, the else path will never happen, this will be clearly detected by this kind of tests. And even more complicated, there is level E, which is MCDC. It's multiple clause decision coverage, and it will fill at least 1 hour to explain that. To summarize it, it's very, you have very high effort for testing that. You have to have look at every parameter in every clause, in every condition, what the result would be. And something else which is very consuming a lot of effort is the source to object code traceability. As was it said now on the high level and low level requirements and the source code, you have here now on object code. So you have to have a look at every assembler line where it belongs to a source code line. You can imagine that's quite a lot of effort. Fortunately, there are certified compilers which are allowed to help you here. Anyhow, a lot of effort. Now, the independence. D178 often states independence. There are two views about that. First is the process view in itself, which says that independent topics will be separated in separated documents, like the design plan and the verification plan and the configuration management plan. They're in separate documents, or at least in separate chapters. And high-level requirements are separated from low-level requirements. Test is separated from specification. But that's not what the D178 intends in here. It intends a personal view. That means dependent artifacts like requirement, code, and test will be done by different persons. And artifacts will be reviewed by different persons than the author. Like if you're writing a source code, then you're not the one who specifies the source code. If you're having a look at a source code or of a test case, then you cannot be the author of that. Review is a very smart method of finding errors in a very formal way, but if you're getting used to that, it's a very helpful process. Also, reviews would take too long to explain in more detail, but if you're interested, I'm happy to explain it in a smaller group. So to summarize that, The DO-178 is a software development guideline which is accepted by the EASA and by the FAA, and that's the reason why the companies are using it. By the way, they are also using it now because they have just seen that it makes sense. But if you develop something which will not be accepted by the government, then you're not very happy with that. By the way, you can develop with a complete different process, but you have to explain why. Small planes often using different processes because they just said that if they crash, not a lot of people are killed, so that's good enough. Yeah, unfortunately. It contains a description of a complete development process, including specification and evaluation. It does not specify how in detail it should look like, but how the interactions in it and what artifacts shall be here. And it relies, beside other things, on the principle that software shall only contain functionality it has to. This is, for example, also very interesting if you just think on test code. Often you have in your software code which is just used for testing it. But imagine a plane which just starts in the air to run his test routines, putting all rudders in all directions and this kind of stuff. It's not a good idea to have that. And it describes a clean requirement coding test development process with an emphasis of independence that has been proven to find a lot of errors. And it has evolved of experiences on 40 years of critical software development and has facilitated a huge development projects like A380 and the 787, which are really, you can't imagine how big they are as a matter of, in case of software, on a very high reliability standard. That's all? No, of course it's not. But, for example, protected operating systems will be used. Time-triggered operating systems and communication will be used. Mathematical proof of substance will be used. This is a very fancy thing, and companies are paying a lot of money for mathematic professors to do that. Also, they're using proven hardware. No one will get a state-of-the-art computer in a plane. And last but not least, redundancy. Redundancy is often used in software and in hardware. But the most expensive thing in a plane is weight. And if you have 3 computers, they will weigh more than 2 computers. Will work more than 1 computer. And if you can just satisfy the function with 1 computer, you will do that. But still, the DO-178B is the spine of the software development. So if you do something, you will be involved with that. Coming to my conclusion, Peter Ustinov just said that being an optimist is to be foolish enough to believe that the best will come yet. Hopefully it will come. Can we use it outside the aerospace industry? It's a complex software development process. It may get very expensive to do testing. So if you have a look at level E, which just is number of 1, then you can imagine what level A means. By the way, this is just the expected and the real thing. Like most of the people think that level B will cost much less than level A, but which is not true, and so on and so on. But as we know, or as history has proven, that formal processes may help find errors early, and finding an error early will get it less expensive. That could be a way to just have the trade-off. Investing money and effort in having a complex and formal process versus finding errors very late. I mean, if it's an application where you don't care about an error and the error in a field would not cost a lot of effort to fix it and not a lot of money, then don't invest that in the development process. But if $1.1 billion, they have invested just one review, you will be rich. So some methods may be helpful, like the requirement tree. I think that could easily be attached also to non-critical software projects. And the independence and reviews. By the way, new programming methods like extreme programming going that way, but describing it different. Maybe there is some interaction. But a full DO178B is not easy to be applied because it relies first of it on a network, and I don't expect any computer to have a DO254 certification for the hardware. And because of the fault tree, meaning what a component can cause on other components, you will probably would have DO178B in all of the components. And imagine Linux fully specified, fully test cased, every assembler line is known where it comes from. I don't think so. But maybe own guidelines could be developed. And the advantage of that is if it's accepted by everyone, then you can use them for multi-site projects. Multi-site in case of multi-components, multi-area, whatever, because they need to trust. If I'm using a component for my critical application, I have to trust all underneath components. So just to conclude, who you can trust, I think accepted guidelines you can trust. But the guidelines are to be developed. I don't see that they currently exist. So that's it. Thank you for your interest. Do you have any questions? Microphone is coming.
What is the most common computing language in aerospace industry?
The funny thing is it's C. Ada has been used quite a while, and it is used. And it is a good language because it gives you a lot of formalism and a lot of checks. But many components are developed in C. Just simple of that. High-level components sometimes developed in C++, but the effort to certify a C++ environment is quite high, so they don't do it.
First, one comment to the previous speaker. I'm not sure if it's true for really safety-critical applications or safety-critical functions that they are primarily programmed in C, because C is not very good for formal verification. And for example, there's Praxis High Integrity Systems in the United Kingdom, which uses Spark, which is an Ada subset with annotations that specify the data flow, information flow, and you can also specify pre- and post conditions and can do a formal verification of the source code. And Praxis is known to achieve industry-wide provably the highest rate of absence of errors. So they have the lowest error rate of any software. For example, they have made the avionics, at least the safety critical parts of the Hercules C-130J, and also the safety critical parts of the avionics of the Eurofighter have been done in Spark. But one other thing, I have a slight problem with the wording of the slides of saying requirements, coding, testing, with the testing part, because in aerospace, some safety critical parts require to be reliable to the point of only one failure in 10 to the 9 hours. That is about 114,000 years. So if you have a fleet with 100 planes, it may not fail once in 1,000 years, the complete fleet. And you cannot achieve that level of confidence with testing, which means testing normally means you look at the system or the module as a black box, you feed input in, and you look at the output and see if the output is correct. And Littlebot and Strygini have shown I think in the late 80s, that you cannot achieve that level of confidence, not anywhere near it, by testing. Yeah. So the DO178B suggests other methods than pure testing, like code reviews and formal verifications, and also suggests mathematical methods, very strongly formal methods. So it's just a question about wording, not to call it testing, but verification might be better.
Yeah, first to the ADA thing, to the development. Yes, you're true. There will be